Greetings and welcome, friends. Mr. Waddy here. Today we are in section 5.4, solving special systems of linear equations. There are some unique cases in which, when you have two lines or two equations and you're trying to find the common points, where some unusual outcomes can occur. So we're going to talk about those special situations today. Right here on the screen now, I'm showing you a chart. This is actually found in section 5.3. But I think it's appropriate to show today because we're going to be able to choose our own methods for solving systems. So you're not locked into using just substitution or elimination. You can use multiple systems, multiple means for solving. And so if I was to ever use graphing, which I don't, graphing is good to estimate solutions, but why would I don't want to do that. I don't want to do that. Graphing is, good for estimating. It's not very accurate. It kind of only works when they're close range to each other. I'll show you some Desmos graphs today, but yeah, graphing by hand is not the preferable way to do things. Solving by substitution was great whenever one of the variables in one of the equations had a coefficient of 1 or -1. So that's like our sniper rifle. We want to aim for the weak spot, and that's anytime you have like x plus 3y equals 1 and 2x minus 7y equals 10, right? I would aim for the variable that doesn't have a coefficient in front of it besides -1 or 1. Aim for the weak spot. Elimination method is great when one pair of like terms has the same or opposite coefficients, or anytime we don't have a weak spot. All right, so that's basically what I would there when there's no weak spot, right? Quote unquote weak, right? And that's when you use elimination method to bust through all that extra armor of those coefficients right there. So let's oh, I did end up accidentally undoing. Let's take a look at some of these special cases. Grabbing a screenshot. Here we go. Put it up on the screen. That's an official jingle of Microsoft's snipping tool. I don't know why they don't advertise more, but if they are and they see my video, they can contact me. I'd love to record my little jingle for their snipping. Core concept. It says solutions of systems of linear equations. Check this out. A system of linear equations, all right, when we have two equations and two unknowns, or we have two graphs and we're finding the intersection, can have one solution. That has been every system we've solved so far, where we find one solution, x comma y, that makes both equations true at the same time. All right, where our solution happened to be the intersection of those two lines. It is, however, also possible to have no solution. All right, why do you think this describes no solution? What do you think? What went wrong here? Why is there no solution if my two lines look like that? Yeah, they never cross. They would never intersect with one another, right? If I'm looking for intersections, I'm like, all right, where's the intersection? Oh, it's not here. I'll just move this way. Nope, it's not there. And I would search for infinity in both directions and never find those lines cross. So no solution occurs when the lines are parallel. Let's see, side note, what are the slopes of these two lines? How would the slopes of these lines relate to each other? What? No. What could you guys tell me about the slopes of these lines? If the slope of line 1 here was, let's say, 2/3, what would the slope of the second line be? 2/3. The slopes will be the same, right? Parallel lines have the same slope, right? Same slope, and that's why they never intersect each other. They've got the same rise over run. It is also possible to have infinitely many solutions, all right? If I'm looking for intersections of lines, and what if my two lines ended up being like exactly the same line? All right, I didn't draw that the best, but imagine that my two lines were exactly the same, and I gave you the task of, tell me when these lines cross each other, and you're like, oh, right here, I found it. Oh, but also, right here's, oh, and right there's a solution, and right there, and I would count every single point on the line as a solution, of which there are infinitely many solutions. Um, well, these lines all have the arrows on the endpoints because they do go on forever. But as far as the infinitely many solutions, it will just occur when the lines happen to be the same. Oop, I hit the button. There we go. Let's take a look at example 1. Now, guys, we've got options here. We can actually choose. What was it? There was, yeah, Halo 4 actually allowed you to like choose a loadout where you could pick which weapons you came to the match with. We get to choose our weapon today, right? It says solve the system of linear equations, and it didn't tell me using blah, blah, blah. And this is great. We finally have the freedom to play the way we want. I love it. All right, so I never want to solve by graphing, but tell you what, let's see Desmos. We'll see what Desmos looks like if I solve by graphing. All right. All right, where am I here? All right, y equals 2x plus 1 is their first equation. So y equals 2x plus 1. There's the first equation like that, and the other one was y equals 2x minus 5. Wait a minute. Guys, look at this. What's going on with these slopes here? They're the same slope, and they have different y-intercepts. What type of lines do you think these are going to be? I think they're going to be parallel lines. And so graphically speaking, we see that these lines, I could keep searching, looking for love in all the wrong places. And this blue line is just like in the friend zone with that red line. He is never going to have a relationship with her. Yeah, like he's like, I want to be so close to you. And she's like, nah, I'm good. Right? And no. Wherever I look, yeah, that is not happening. See, what happens if I click? Oh, default zoom. Nice. I didn't even know that was an option. Wow, lovely. Yeah, and then I can just, bam, pop me right back to start. All right, so I'm anticipating that these will have no solution. Graphically, we understand what that looks like, but what will that look like when I try solving? Huh. So let's try. I'm going to solve by substitution. Why do you think I'm choosing substitution here? Yeah, because there's two excellent weak spots, right? I could solve for this y or this y, right? Both of those have a positive 1 coefficient. Let's see what happens. I think so. Step 1 for substitution is solve one of the equations for one of its variables. Already done. Y equals 2x plus 1. Done. All right. This was already solved for y. Actually, I'll highlight that just because I like to show where I'm targeting with my reticle. You guys know that what a reticle is? Reticle is like the little crosshair when you're playing your video game and where you're aiming. Reticle. Also, my oldest son's name is Everett, also known as Rhett, and maybe one day his gamer tag will be Reticle. So here was the idea for substitution step 2. If 2x plus 1 is really equal to y, that means I could plug it in to the other equation for y and maintain equality. All right, so step 2, let's plug that in for y. So I'm replacing that with y. I don't need to put parentheses around it because there was no like multiplication, in front of this y. So I'm just going to write 2x plus 1 equals, and it's equal to 2x minus 5. And let's see, step 3 was to solve that. Okay, let's bring these x's together, friends. Oh, x's are on both sides of the equation, so I've got to move one. I'll move the little guy to the big guy, but wait, they're the same size guy. They're both 2 x's. All right, well, let's just try moving one, and we'll see what happens. And I get, what happened here, friends? 2x, I get 0, I get 1 equal 0. 1 equals negative 5. Guys, I was trying to solve for x and y, and all that came out was 1 equals negative 5. What's happened to my variables? Oh man, guys, I don't know what happened. I think I just broke math. I eliminated them, exactly. Actually, Brandon, you did have an interesting thought. You said there would be a divide by 0. But now, technically, I've come to a conclusion. Let me show where kind of that makes sense, because I've never thought of it from that perspective. 2x minus 2x is 0 x's, right? And let's say I wanted to solve for x. Wow, I've never thought about it this way. You guys don't have to write this down. Just like my own investigation. If I want to solve for x, I would have had to divide both sides by 0. Huh. And I get x is undefined. Yeah, that's impossible. Wow, I've never thought about it that way. That's just showed me a different way of thinking about the math here. But the way I had this turn out was I got 1 equals -5. Now this is a false statement, right? I hope you guys agree that 1 is not equal to -5. Okay. All right. Whew. All right. I mean, if we're not there, then we've got to take some time in ACE to really review that. So 1 is not equal to -5. Therefore, there are no solutions. No solutions. So when your variables disappear and you end up with a false statement, you conclude that there's no solution. And actually, the same thing would have happened if I tried to solve using the elimination method. Maybe I'll do that for one of these other examples where there's no solution. The variables would all disappear, and I'd end up with a false statement. So when I'm solving using substitution or elimination, this is what it looks like when I have no solutions. When I'm solving graphically, this is what it looks like when I have no solutions. I have 2 parallel lines. Okay? You guys buying that? That special case right there? Yeah, that makes sense. All right, let's take a look at this next example. Example 2, conveniently, aptly. Questions, comments, or? All right. Gonna solve a system with infinitely many solutions. Spoiler alert, infinitely many solutions. We even looked at a graph of this problem real quick, and you saw that these represented the same line. So graphically, that's what happens. But what does that look like when I solve algebraically by either substitution or elimination method? Question, which method should I try solving this with? What do you recommend? Neither. Neither. What? Well, one of your methods is going to be substitute, or it's going to be one of those, I'm pretty sure. And then you just had like the divide by 0 thing that was at the tail end of it. Let's see. Well, looking at this, is there a weak spot that I could target? Well, I mean, that would create fractions. Yeah, the y in the first equation has a +1 or a -1 coefficient, right? In this case, it's positive. And so that's what we call a weak spot. So we'll solve by substitution, all right? And we'll see what happens and how that would have clued me into the fact that this has infinitely many solutions. So step 1, solve one of the equations for one of its variables, and we're solving this first equation for y. So I would add 2x to both sides, and I'll have y equals 2x plus 3. Hopefully you guys are masters of solving systems these days. We're using all of our tools in our toolkit. And so if y is actually equal to 2x plus 3, that means I could replace this y with that expression. And why is that helpful to us? Well, it's helpful because I'll have an equation, a single equation, written all in terms of x. So that's step 2. And for step 2, you always have to plug it into the second equation. Do not, all right, this is super illegal. Do not plug it into the equation you just solved for. All right? No. All right? Don't do that. Super illegal. You will actually, in doing so, falsely have given yourself this conclusion. Every single system, you would have falsely given yourself the conclusion of infinitely many solutions. No. It would give you like a false positive. Like, if someone took a pregnancy test and said they were pregnant but they weren't, that's called a false positive. If I plug this into the original equation I solved for, it will tell me I had infinitely many solutions, even if I only had one, or even if I had no solutions. So it's not a good test when it fails every time. Right, but in this case, you don't want infinitely many babies. So let's see, plus 2 parentheses. But not infinitely many. Yeah, so, yeah, they stopped counting after 19, apparently. All right, so guys, I'm distributing. Oh, error. So anyways, we don't have a lot of time, so we're going to talk about these infinitely many solutions. So notice I distributed 2 times 2x is 4x, 2 times 3 is 6. What happens when I combine these like terms here? Negative 4x plus 4x. I get 0 x's, or just 0, or just, I won't even write it, and I'll get 6 equals 6. So when I'm trying to solve for x and y that makes this true, all my variables disappeared, and I was left with a true statement. And what that statement tells me, my conclusion is, right, because it's true, that's a terrible R. True. There we go. Therefore, there are infinitely many solutions. Infinitely many solutions. Okay, so that's what it looks like when I have infinitely many solutions and I solve algebraically. My variables disappear, right? They killed each other, and I'm left with a true statement. If I'm left with a false statement, that means I have no solution. No solution, right? So you guys remember that from yesterday. Okay, let us do... do I have a... no. Tell you what, I'm just going to do example 3. I was going to do another let's do one more. Let's do one more. Do you guys, I think I gave you guys 1, 2, 3, or 4. What's a good one you want to do? Did I give, on your sheet, do you have 1, 2, 3, and 4? Actually, I can check. Yeah. Which one do you guys like? Pick one of those. 2. Okay, I was going to, if you guys weren't going to pick one, I was going to roll one of my 4-sided dice, and then that would have selected for us. All right, so let's take a look at question 2 together, just to have one more example like this. Now, I don't know how many solutions this has. All right, I don't know. But we're going to solve algebraically and see what we get. What do you guys think? What method should I choose to solve? Move the 2x? So you want to solve for this y? We could solve for the negative x. This is a weak spot. Even better, though, we don't even need to. Look at this. Austin, if you're thinking of elimination method, yes, you are actually 100% right. Yep, I see where you're going there. I'm going to use substitution again. Subs. And solve for this y. The convenient thing about this y, not only does it have a positive 1 coefficient, but it's also already solved for. Step 1 is done. Y equals negative x plus 3. It's already solved for. And now, if that's truly equal to y, I can plug it in for y in el otro equation. So let's see, 2. So I'll have 2x plus 2 times negative x plus 3 equals 4. Like so. Let's do some distributing. And I'll have 2x. Here we go. Sorry, 2 times negative x would be negative 2x. 2 times 3 is 6 equals 4. Combine some like terms. Guys, I'm sad. These like terms, they fell in love, but it's like kind of a Romeo and Juliet situation where they both die. Ugh, that's sad. And I'm left with 6 equals 4. Not true. That's a false statement, right? 6 does not equal 4. So what is our conclusion? No solution, right? Graphically, what would I expect these lines to look like? Parallel. And parallel lines, how do their slopes relate to one another? They're the same slope and they have different starting points, right? So, I just want to point out another way you could do this problem is to analyze, right, slope-intercept form is another way that you can do some of these problems. All right, so the first one is y equals negative x plus 3. And so what is the slope here? The slope is the number in front of the x, which is negative 1, right? mx plus b. And what's the y-intercept? Yeah, the 3, the plus b there, right? And let's see, could I write the other equation in slope-intercept form? 2x plus 2e is equal to 4. And this is when I would do what Austin was describing earlier, subtracting 2x from both sides to get y. Negative 2x plus 4. And then what would I do to get y completely by itself? Being multiplied by 2. How do I undo multiplication? Yeah, division, yep. So everybody divided by 2. And I'd have y equals negative x, right? 2 over 2 cancels out, plus 2. So here are my two equations, and I'm looking for the solution to their system. What is the slope of the second equation going to be? Negative 1. And what is the y-intercept? B equals 2. So notice that because, all right, because these slopes are the same slope, that means that these lines are either going to be parallel or the same line. And because they have different y-intercepts, all right, different, therefore they are different lines, and those two things allow me to conclude that they are parallel lines. All right, and therefore no solution. Right, there would be no intersection between two lines that are parallel. Oh, that's a whole different problem. We'll get there later, but these are linear equations so far, linear systems. But yeah, there are ways to solve systems with crazier, curvier, swoopedier graphs as well. So there is a way to also kind of do these problems by analyzing your equations when they're in slope-intercept form, and just kind of visualizing the graph without ever having to do the work of graphing them. So let's see. Here's example 3. This will be the last example we do today. Ooh, we've got a picture of some gardens or something, or parks. Oh, a piece of land. Here we go. All right. Piece of land. Ooh, 2 pieces of land. Actually, I've got to figure out... No, my land is like some irregular shape. I own 1.3 acres, or actually the bank does, but they let me live there. It says the perimeter of the trapezoidal piece of land is 48 kilometers. All right, so if I add all those up, it's equal to 48. So could you write an equation like that? Let's see. Well, let's do that. So 2x plus 6y plus 4x plus 6y. Did I get all of them? 2x, 6y, 4x, 6y equals what? 48 kilometers. All right, so there's one equation. You don't have to do that yet. I think that's a great idea, Austin. Let's combine like terms, right? So yeah, we'll simplify that equation. 2x plus 4x is 6x, and 6y plus 6y is 12y. That equals 48. So there's our first equation. All right, it says the perimeter of the rectangular piece of land is 144 kilometers. All right, and that 18x came from combining the 9x's. Does anyone know another way you could have written the original equation on this one? I could have said 2 times 9x plus 2 times 8y, since, right, these two sides are congruent and these two sides are congruent. I could have just doubled this plus double that, and that's the same thing. But either way, that works. Plus, yeah, we said 36y equals 144. Why do we need this square root? Well, I mean, if we had squares or something, we could... but although that wouldn't help us, because that's actually only area. We're talking perimeter, which is the sum of the sides. And then it says, write and solve a linear system of equations. So I've got 2 equations here. Tell you what, I'll even rewrite the other one again. What way should I try to solve this system? So you're thinking elimination method? I think that could work, because, yeah, there don't appear to be any weak spots. All right, let's do it. So, for the x's, what is the least common multiple between 6 and 18? What's the smallest number that they both go into? I believe that's 18. 18 goes into itself and 6 goes into it. And how about for 36 and 12? Yeah, 36 goes into itself and 12 goes into that 3 times. So we'll pick 18. We'll shoot for opposite x's. We're using the elimination method in case you're wondering why I'm even asking these questions. This equation already has an 18, so that one's all set. What would I have to multiply 6 by to get it to be 18? I'm shooting for opposite x's here, right? 3. And bless you. And I want it negative because this one's already positive and I want this one to be negative, so -3, yeah. So let's see. So let's distribute this. -3 times 6x is -18x. -3 times 12y is -36y equals... well, no, it won't matter. We're just distributing. And let's see. And I get -3 times 48. I reached for my calculator on that one, is -144. So if I want to add this equation to this equation, what? That's crazy. I'll even rewrite the other equation again. You don't have to do this, but I will. So that was step 1, right? And now step 2, I'm adding them up. 0 plus 0 equals 0. I get 0 equals 0. Is that a true statement? Yes. So that means that there are infinitely many solutions. Crazy. Infinitely many solutions. Now, that does not mean that every combination of x and y works. The only ones that work are the ones that are represented by either of these equations. All right? So I'll just say, like, solutions that make this true, 6x plus 12y equals 48. And let me show you what some of those solutions look like. I'll pull up the Desmos calculator real quick. 6x plus 12y equals 48. 6x plus 12y equals 48. And so there we go. The solutions are, I doubt we would consider negative solutions as a possibility. But there are infinitely many solutions nonetheless, and the solutions are all of these points on this red line, okay? So if I wanted to find the possible combinations of x and y that make this true, right, that would result in both of those perimeters for both of those shapes with these given proportions of those shapes, right? I could pick solutions like this one. Here, I'll use the classic purple, right? So this solution would be 2, 3. All right. Here's another solution, 4, 2. All right. Here's another solution, like 6, 1 would work. All right. Or this one doesn't make a lot of sense. 8, 0. Would 0 work for y? Could I have a rectangle that has 0, because 18 times 0 is 0, as 0 is one of its side lengths? No, that doesn't work well for land. No. So that means this point doesn't work, but everything probably between these points would. But also, you wouldn't want a super skinny piece of land that's like 0.00001 acres, or not acres, feet wide or whatever. It would just be like a super long and skinny piece of land that happens to be like 144 acres. It would be super inconvenient. Yeah. But also, I just want to point out solutions like this one work. 1.5 comma, looks like 3.25 maybe. And all of the points in between here. So there are infinitely many solutions that would work for this system. All right, well, thanks for watching, internet friends. Have a great day. Bye-bye.